or efficiency.
It's my pleasure to present my talk. Well, my talk is pretty much along the same lines with that of the Professor New of our previous presentation. So the title of my talk is the cellular greening via efficient BS control from the topology, on-off, and transmission power. This talk is talking about the BS control policies for greening. And typically, I think about a lot of problems in this domain according to different timescales. So I'm going to present based on those criteria. And also, this talk is biased on the algorithmic solutions, not the practical protocols, and also biased with some academia works. And this is based on my recent researches and also my colleagues' researches. And I really apologize for the missing references, especially the paper by Professor New. So I generally assume that because this is often firms, when I was invited, I was trying to imagine what are the audience. I just assume that the general IT audience, not the greening expert, because I'm not the greening expert. And this is a special thanks to my colleagues and the co-authors of the papers. All right, I guess a lot of people were talking about these numbers and so on, and probably this number has been changed now. So the summary of these numbers is that, okay, we're consuming from the 2 to 10% of the energy in the ICT industry, and then in the mobile communication, we are spending about 9 or 10, which is increasing, I guess. And also the BS is using a lot of powers out of those mobile communications, so that's why it's very important to have energy efficient control mechanisms of the BS. Again, greening needs are coming from the environmental as well as the economic issues. Let me skip. Probably I have to speed up my presentation in order to follow the schedule, right? So everyone likes that kind of pattern. There are many, I guess there are many spots for greening, right? I mean, this is not just, so I'm just, well, this is my special focus on the spot of greening when I do the research about the greening. So one thing is that, well, of course, it's possible to improve the existing network performance by developing new technologies and so on. So that's true. For example, like a large-scale smart antenna system is one of the examples in the demonstration of this GreenTouch Consortium. But in also many cases, we have to do the trade-off between the performance and energy, right? So in the performance and energy trade that we typically see, so how can we do the greening? So in that case, well, we have to find the spot where it shows the kind of concave performance and energy trade-off, where, as you can see, that here, all right. So here, even if when we decrease the energy a lot, but the performance loss is not that much. So that's the spot that we can find the greening in the wireless system, or probably in many systems. So I'm looking for those spots in many cases. And also another sort of thing that I really think that which is important is that there is something called the resource consolidation, right? So depending on the traffic patterns, as the Professor New says, that the traffic patterns or the usage patterns, so that we have to dynamically adapt the network operations, so that sometimes we have to turn off, turn on, and so on. So those are the two important greening spots, even if there are more greening spots. So I'm really focusing on these two guys. We know the statistics, right? So we have to use this resource consolidation scheme. So when we look at the cellular networks, this is how we look at for greening the BS cellular system. So we have a lot of control mechanisms, and which has a different time scales. So for example, if we employ or deploy the BS topologies, and probably we cannot change the BS topology for some years and so on. Well, depending on what kind of BS we are using. Probably for example, like a femto cell can be changed at any time. But typically, like when we talk about the macro cell, macro base station, that it typically, if we install, then it will be sustained for like at least 2 or 3 years, right? So starting from the BS topology, and then we can do the BS switching on and off. That probably we can take with the time scale of order of hours, and the BS association is just a little bit less than the hours, so we can do that like in the minutes when the mobiles are moved from the one cell to another cell. Then we have to change the BS association. Or in the next, or probably today's cellular systems, cell sizes are becoming smaller and smaller. So it's very important to control the interference. For example, like how can we guarantee the performance at the HE guys? And then interference control is a very important mechanism where the power control is major resource control mechanisms. And also in the MIMO technique, for example, the new kind of physical layer technique. And also we should do the user scheduling, right? So ranging from the order of years to the order of milliseconds, we have a lot of control mechanisms. So when I look at this various timescales of the resource mechanisms, how can we coordinate those multiple resource controls so that we can achieve some greening? So this is one of the directions that I look at the system when I do the greening research. And this is the problem space that I look at. Of course, well, this is just one figure that I draw. So when you look at that, then I just think about the 3 axes or the dimensions, where the one dimension is the space. So where do we have to focus on, right? So starting from the backhaul network to the base station to the mobile terminals, there could be many places for reducing the energy. And another dimension is control mechanisms, or resource management, right? So it means that how and how often. So again, depending on the time scale, infra deployment will take a few years, and then BS on-off or the transmission power control. So we have a different time scales and different topics to control. And also another axis is the performance metric, right? So we have a lot of metrics. So for example, like a voice over IP traffic will be heavily dependent on the delay performance, or the file transfer traffic will be heavily dependent on the throughput. So we have various levels of the performance metric, or you can call it QoS. And also sometimes we need to consider the fairness, meaning that when we make the greening policies, then 2 or more mobile network providers are involved, right? So probably they are very selfish. So how can we guarantee the fairness among those mobile network providers? So that's a fairness issue. So space, performance, and the control things. So which spot or which point do we have to place? So depending on the quality of the greening policies, we can achieve the very nice, sometimes trade-off points, sometimes some point in this 3D dimension. So this talk, the remainder of this talk will be focused on some 3 case studies that some part of which will include me as a co-author, and then I just use some of my colleagues' research in order to show that there are some. These are the examples from the BS topology design to the BS transmit power control. So it's like order of years to the order of milliseconds. Right. So first thing is that the paper that the Professor New mentioned. So I'm going to BS topology design again. Well, sorry for the missing references. There will be a lot of references. So I just put the 2 papers here, and then as you can see, there are many performance metrics in the y-axis and the x-axis. Is that depending on the system model. Okay, what kind of systems that we're considering, we can have many research results. So here, this paper is talking about this problem. So the input for the problem is that, okay, macro base station probably is very difficult to change, right? So we have to have them. But the micro base station, well, they think the micro base station can be installed when there are more needs about the network capacities. So as the smartphones popularity is increasing, then we have to install the micro base station. So their problem is that given the macro base station and also given the kind of performance enhancement factor, meaning that okay, we have to increase the current capacity by the factor of 1.2, 2. Okay, so that's the given from some study of the customers. And then how can we deploy the micro base stations in some places in order to achieve the sort of the biggest energy efficiency? So here the biggest energy efficiency means that essentially how can we minimize the number of micro base stations in order to satisfy the performance enhancement factor? So that's their problem, right? Oh, there's the animation. Okay, I didn't know that. Okay. All right, right. Yeah, sometimes I forgot how I make my slides. All right. All right. So well. Even if this is a mathematical expression, so well, I don't like math, so don't try to focus on this math. I mean, this is just one of the problem formulations that they're looking at. Again, the problem formulations were explained in the previous slides, and then if we look at that, just roughly look at that. Okay, these are if we look at the time scale of the 1 day. So how can we, and then suppose that we decompose the 24 hours into the 1 hour slots, then how can we find a sequence of the active base stations? Active base station means that the base station should be turned on. And then we have to minimize the total power consumption where the BTM, cup, BTM, small m, this is a macro base station sets, and this is a micro base station sets. The cup of union of these guys should be the BT. And how can we make the sequence of the active set sequence so that we can minimize this guy? But the constraint is that this zeta is the performance improvement factor. So this is the average flow level throughput that currently we can get with the current deployments, and then we're gonna increase by the factor of zeta. So this is a constraint. So how can we solve this problem? So this is just one example of the problem formulation. And what they do is that, again, don't try to follow up all the equations. So what they do is that, all right, so probably the BS deployment time scale is different from the BS on-off operation. So they think about the joint solution of the micro BS deployment and the BS operation problem. So they first find at which places do I have to deploy of the micro base stations in order to satisfy the the required capacity increase, where they look at the peak time of the daily traffic. So based on the peak time of the daily traffic, they first determine which places, and at which places do we have to deploy the micro base station. And for the added the micro base station, they find what are the patterns of the on and off over time. Okay, so it seems reasonable to achieve the objective. And this is a simulation where basically it means that if we want to satisfy the requirement performance increase using the macro base station with, for example, the transmit power is about 20 watts, then we need 10 guys, which means 200. But if we use the micro base station, then we need like 50 guys, but multiplied by, but these guys is using just 1.5 watts. So if we measure the total the energy consumption, and if we compare with the micro base station deployment and the macro base station deployment, we can see some significant energy saving. That's what they are talking about.